Your FastMCP server holds the data you need, but how do you actually pull it in and work with it in your code? We'll see exactly how to read both text and binary resources from a server, then handle their contents properly, whether you're processing configuration files or downloading assets. The pattern works for any resource type, and you'll use it constantly in real-world applications.
Async with client. Hash read a static resource. Content equals await client, read resource. File, //path/ to /readme, MD. Hash content, list MCP types, text resource contents, MCP types, blob resource contents. Hash access text content. If hasheader, content 0, text. Print content 0, text. Hash access binary content. If hasheader, content 0, blob. Print F binary data. Len content 0, blob, bytes.
This demonstrates the resource abstraction pattern for unified content access. The code shows how FastMCP standardizes interactions with diverse data sources, whether static files, dynamic templates, or binary assets, through a single consistent interface. What makes this distinctive is its protocol-agnostic design, where URIs become the universal addressing mechanism regardless of the underlying storage system. The pattern works by treating all resources as typed content streams, with the client handling content negotiation automatically. Text and binary data share the same access method, but return specialized objects, text resource contents or blob resource contents, that expose appropriate attributes. This polymorphism lets your code remain oblivious to the physical storage details, focusing instead on content semantics through type checking via hasheader. This approach solves the fragmentation problem in multi-protocol systems, where you'd otherwise need separate clients for file systems, APIs, or databases. It's particularly valuable in microservice architectures or tooling that must aggregate data from heterogeneous sources. The trade-off is a slight abstraction overhead, but the gain in maintainability and reduced coupling typically outweighs the cost for most applications. Let's break it down line by line.
Async with client.
This establishes an async context manager for the MCP client connection. The pattern guarantees proper resource cleanup when the block exits, preventing connection leaks. All MCP operations must run within this context to ensure reliable server communication.
Hash read a static resource. Content equals await client, read resource. File, //path/ to /readme, MD.
This fetches static resource content from the MCP server using a file URI. The await handles the async operation, returning a list of resource contents that may be text or binary. This is the standard pattern for reading resources in FastMCP, where URIs can reference local files or remote storage.
Hash content, list MCP types, text resource contents, MCP types, blob resource contents. Hash access text content. If hasheader, content 0, text.
The type annotation indicates content is a list containing either text or binary resource objects. The hasheader check dynamically verifies if the first item has a text attribute, enabling safe access to text content without assuming the resource type. This is defensive programming for handling heterogeneous resource responses.
Print content 0, text.
This outputs the text content from the first resource in the response. The hasheader check above ensures we only access text when the resource contains text data, preventing attribute error for binary files.
Hash access binary content. If hasheader, content 0, blob.
Dynamic type safety check uses hasheader to verify the response contains binary data before accessing the blob attribute, preventing attribute error if the content is text only. This defensive pattern handles both text and binary responses from the same endpoint.
Print F binary data. Len content 0 blob bytes.
This outputs the binary data size in bytes, providing a quick verification of the downloaded content. When working with blobs, checking the byte length is often the first validation step before processing or storage. Resource polymorphism in FastMCP. The same read resource call handles both text and binary content through type-aware response objects, with hassetter dynamically routing to text or blob attributes. The URI scheme determines the server context in multi-server clients, not the resource type. This pattern eliminates conditional branching in client code while preserving type safety.
The resource that answers every question answers none.